When you're working on a project with tons of simulated entities, storage is a huge deal. The right data structure can make your simulation fly, while the wrong one can completely tank your performance. In this video, I'm going to show you the container I use to store entities in pretty much every project I work on. We are looking for a structure that supports fast insertion and deletion of objects, efficient access to specific entities, and stable identification. This means that every entity retains a unique, unchanging ID that can be used to retrieve it. A first option might be to use a vector. Vectors are dynamic arrays, meaning that they allow us to easily add new objects to the end of the container. They also provide constant time access via an index. To hold a reference to an object within the vector, we might consider simply use a pointer. As a reminder, a pointer is nothing more than a number representing a memory location, an address. For example, if the object at location 15 is a pointer, then its value, in this case 28, represents another address. To access the value referenced by the pointer, we must therefore look at the contents of location 28, which is 5. Thus, accessing the value behind a pointer, known as dereferencing, simply means reading the data at the memory address stored within the pointer. With our vectors, we might therefore be tempted to use a pointer to identify an element and access it later. While this sounds like a good idea, issues will arise very quickly. Vectors are contiguous in memory, meaning they store their data in a single large block. But what happens if there isn't enough room to expand when adding a new element? In that case, the vector reallocates its data to a new memory space with sufficient capacity. However, during this process, all pointers to the objects become invalid because they all have been moved to new addresses. A fairly simple solution would be to use the object's index to identify them rather than a pointer. Since the order is preserved, the indices remain the same even after reallocation. Unfortunately, this approach doesn't work either. Being contiguous in memory comes with another annoying side effect. A vector cannot contain holes. This means we can't simply delete an element from the middle. If we do, the data is automatically shifted to fill the gap. This operation has two downsides. It is computationally expensive, and it also invalidates all the indices following the deleted element. For example, in this case, the element at index 4 now corresponds to the former element from index 5. To summarize, vectors allow you to append elements quite quickly. However, this operation can trigger a data reallocation, which comes at a cost. Deleting an element is expensive because it forces a shift of all the data that follows. On the other hand, accessing a specific element via an index is very fast, but indices aren't stable, meaning they get invalidated whenever elements are deleted. So, our vector seems to be causing a lot of trouble. What other options can we explore? The other star container is the list. Just like a vector, a list lets us add elements on the fly very quickly. It's actually even faster than a vector, since lists don't store elements contiguously in memory, meaning there's never any need for reallocation. So we can safely use a pointer to access an element. It will never be invalidated. The same goes for deletion. Lists operate via a bidirectional chain of pointers between elements. This makes deleting very fast because it only involves updating a few pointers, an operation that is completely independent of the number of elements in the list. And once again, this operation doesn't invalidate any pointers. To sum up, the list allows us to add elements very quickly and easily. Removal is very fast and independent of the number of elements present. However, we cannot directly access a given element by index. Indeed, the only way to reach the nth element is to traverse the list from the beginning. On the other hand, pointers are never invalidated, so they can serve as stable identifiers. Comparing this result with the vectors, the list seems to be the undisputed winner. Aside from accessing a specific value, which requires a pointer, there is no debate. And yet, What seemed to be the vector's biggest flaw was actually its greatest strength. To demonstrate this, let's compare the time it takes to sum the elements of a list versus a vector. The test is very simple. We will iterate over all the elements, 1 million in this case, and sum them into an accumulator. Once the operation is complete, we will measure how long it took. We will run each test 1000 times to gauge any potential fluctuations. Let's look at the results. As for the list, traversing and summing the elements took 7 milliseconds. It is difficult to judge the speed of such an operation without a baseline for comparison. In your opinion, how does the vector measure up? Well, it turns out the vector is about 20 times faster in this test, taking only 360 microseconds. Moreover, the vector is extremely consistent from one run to the next, with virtually zero fluctuation. The same cannot be said for the list. This test remains very basic and somewhat theoretical. Now let's see what happens when, instead of summing numbers, we iterate over small structures describing physical particles. For each of them, we will execute a very simple update function. As in the previous test, there will be 1 million entities to update. Without further ado, let's look at the results. With the list, the process takes an average of 17 milliseconds. As for the vector, the difference is once again significant, as the same operation takes only 800 microseconds. And, just like with the sum, the fluctuations are minimal. In this test, which is closer to a real-world scenario, the list is once again 20 times slower. But what explains such a stark difference between the two? The answer lies in memory and how the processor utilizes it. When we read data from memory, the processor also loads adjacent elements into an internal cache. This cache is small but extremely fast, allowing for much quicker processing. If the next piece of data we need is already within the cache, accessing it is virtually instantaneous. Conversely, if it is not found, the cache is invalidated and must be reloaded. This is known as a cache miss and incurs a significant time penalty. The key takeaway is that the processor operates much more efficiently on data stored close together, as it benefits from being in the cache. In light of this, we begin to understand why processing data stored in vector is so fast. The elements are placed next to each other in memory. While this characteristic is restrictive for several reasons we have already discussed, it makes vectors extremely cache-friendly. Iterating over a vector means fully leveraging data locality and, consequently, the speed offered by the cache. Conceptually, iterating over a list appears similar to iterating over a vector. We are essentially just traversing elements one by one. However, under the hood, it is a completely different story. Because the data is not contiguous, it is scattered across memory. As we might expect, this is already poor for cache efficiency, but that's not all. Each element in the list carries additional data regarding the list's internal structure, most notably a pointer to the next element. To iterate over the list, we must read the current data and then the pointer to find the next location. We then jump to that address to read the next item, likely triggering a cache miss in the process, and so on. It becomes clear then that this pattern of jumping from one element to another is detrimental to data locality and, by extension, to performance. So, how can we combine the strengths of lists, specifically fast deletion and stable index, with the cache friendliness of vectors? Is there even a solution? Yes, there is. Let's see how to build our own magic container. If you enjoy these highly technical topics and want to deepen your knowledge, I highly recommend Code Crafters. The concept is brilliant and straightforward. You'll be coding essential tools completely from scratch yourself, such as a shell, an interpreter, or even Git. This offers the dual benefit of working on concrete advanced projects while gaining a deep understanding of these tools. The implementation is guided step by step, and with every push, you'll receive instant feedback and advice. To get started, use the link in the description to get 40% off the annual subscription and support the channel at the same time. Let's get back to our container. First, we saw earlier that deleting elements from a vector is slow because it requires shifting subsequent elements. However, there is a trick to speed things up significantly. There is one specific element in a vector whose removal requires no shifting at all, the very last one. Indeed, since nothing follows it, removing it is trivial. The trick, then, is to swap the element we want to remove with the last one, and then delete it. This procedure is known as swap and pop. The term pop simply refers to removing the last element from a container. We now have a vector that allows for very fast element deletion. However, the keenest among us will have already noticed that this still creates indexing issues. Indeed, in a contiguous container, deletion inevitably causes at least one element to move. But there is a solution, and this is where things get interesting. We will continue to store our elements in a vector, which we will refer to as data. However, we will not access its content directly using a raw index. Instead, a second vector, which we will call data index, will store indices pointing to our actual data. Therefore, an element is identified, not by its location in data, but in data index. For example, to access the element with ID 3, we check slot 3 in the data index vector. There, we find the position within the data vector where the target value, in this case D, is located. Now, let's access element 0. Just as before, we look at slot 0 in data index. This redirects us to index 4 in data, which contains A. The advantage of this indirection is that if elements are moved, we simply need to update their location in the data index vector. As a result, the ID remains unchanged and always points to the correct data. Let's see how to remove elements and update the indices. To do this, we need a third and final vector, which we will call ID. This vector acts as the inverse of the previous one. It allows us to map an index in data back to an ID. Suppose we want to remove the element with ID 0. The data index reveals its actual location, A, at index 4. We then swap it with the last element, here C. To keep the ID vector synchronized, we apply the same swap to it. We then use this vector to identify which two entries need updating in data index. Position 6 for A and position 4 for C. We then actually delete A. As we can see, thanks to this system, ID2 still points to C, even though C has changed its position within data. Let's consider another case. Removing ID7. Its data is located at index 1. We swap it with the current last element, which is now B. We also swap the IDs to maintain the correct mapping and use it to update data index. While deletion involves a few steps, they are lightweight and, most importantly, independent of the total number of elements in the vector. Now that we have covered deletion, which is the most complex case, let's look at how to add values. When a value is added to the container, it must return an ID to enable future access. In this instance, we can see that some IDs have been released by previous deletions. When adding a new element in this scenario, it is naturally assigned the ID found at the corresponding index in the ID vector. Here, H would take ID 6 and I, ID 0. If no space remains, meaning the size of data equals that of ID or data index, we append an element to each container. The new ID then corresponds to the container's previous capacity. I chose to split the information into distinct vectors to ensure that we use only what is strictly necessary for each use case. To simply iterate over all elements, we only need data. In this scenario, performance is identical to that of a native vector. Accessing a specific ID requires the additional data index. While this is inevitably slower than a standard vector, it remains very fast, especially since this type of lookup is generally far less performance critical than iteration. Finally, removing an element requires all containers. This is naturally the most expensive operation, though it remains fast. Furthermore, it is generally less critical than iteration or access. We have now covered the operating principles of this container, along with all the basic operations. This container allows for rapid element insertion, though reallocations may still occur. Deletion is significantly faster than in a naive vector implementation. Index access requires only a simple indirection, making it a lightweight operation. Furthermore, iteration is just as fast as in a native vector. And of course, it provides stable IDs for accessing elements. There are obviously countless ways to implement this container. If you want to see the version I use, it is available on my GitHub. Feel free to join the Discord server or Patreon if you want to support me. All the links are in the description.